Hi, thank you everybody for coming. I hear that this is the first of these lectures in this auditorium, so we'll have to deal with the fact that some of you see a different screen than I do. So originally I thought of talking about adventures of reinforcement learning in the real world from one direction, which is the direction of the real world is very, very complex, and in order to learn efficiently and to make decisions efficiently, we have to whittle down our representations to the essentials, to the important essentials, in order, and work only with those. I decided in the end to not talk about that side of my work, although Jerry talked about that, so I wanted to make the connection here and, of course, make the connection to my title, but talk about something a little bit different, which is when we think about what to decide on, sometimes the most important things that we need to include in our representation are actually not available out there at all. It's not that there's too much stuff and we need to whittle it down. It's we need to add something unobservable to the things that we see. And that's what I'm going to talk about. So let's start with the classic Pavlovian conditioning. So we all know this setting. There is, this is Pavlov up there, and he trained dogs by showing them a stimulus that was neutral to start with, let's say ringing a bell, and following that with food again and again. And what we know in this situation is that after a while, the dog learns that the tone predicts the food or causes the food in some way. And we can measure that by knowledge by playing the tone and seeing that the dog slobbers. And this seems like a really simple story. So we have a stimulus that started with neutrality. So we can say it had a value of 0. And over time, its value increased through learning, and now it predicts this take. So why am I telling you all of this? Why am I starting from this? Well, the reason is I'm not sure that that's exactly what animals are learning in this situation. So what do animals really learn? Why do I think this is not what animals are learning? So here's another scenario that's used a lot in research these days called fear conditioning. So you take a rat, you put it in a box, and you play a tone again, but the tone at the end does not lead to a stake. Instead, it leads to a shock, a foot shock. And this kind of conditioning is very, very fast and potent. You can do this pairing once. If you really want to, you can do it 3 times, but once is enough. And the rat will fear the tone. So once you play the tone again, the rat will freeze, showing its fear. And people use this paradigm as a model for strong traumatic memories, for instance, in post-traumatic stress disorder or phobias. And the question is, once the animal has learned this association between the tone and the shock, how do we make him unlearn it to cure his phobia of the tone? And one easy way to do that, and kind of the first thing that would come to mind is, let's play the tone many, many times without a shock, which is what is called extinction. So you extinguish the association between the tone and the shock. And you see that indeed over time, the rat freezes less and less to the sound of the tone. So we can declare success. The rat is no longer afraid of the tone. The problem is that is not true. So if you wait 30 days, or less than that, 28 days. If you wait a while and put the rat in the box and play the tone, the rat will freeze again, showing that that memory is still there, even though it was not exhibited here. Or you can do something else. You can, if you don't want to wait 30 days, you can just give the rat a reminder shock without a tone at all. Just one reminder shock, and then test whether the rat freezes compared to a rat that did not get the reminder shock. And again, after a reminder shock, the rat will freeze a lot more than without the reminder shock, which shows that there was something to remind the rat of. So our story of there was a stimulus with a value of 0, that was this tone. Over time, it came to predict the shock. And as it came to predict the shock, we can make it unpredict the shock. That story is wrong. So what is really going on here? So my former student, Sam Gershman, who just now started his own lab at Harvard University, had the idea that maybe we've been underestimating animals completely. And they might not be learning what we thought. So we thought that they were learning that tones, sorry, I can't point with this, that tones cause shocks. But as you know, tones don't cause shocks. That would be untrue for the animal to learn. In fact, what happened was the experimenter, latent, a hidden cause here, caused both the tone and the shock. And so the true causal structure of the environment is not one in which tones cause shocks. Thank you. I prefer to jump, but but this is a truer depiction of reality. So the idea is that animals are not just willy-nilly relating observables in the environment. They might assume that there are some unobservables, some hidden causes that behind the scenes cause things. And we do that all the time in our daily life. We do that as scientists, but we do that as people. We don't have to have all our causes observable. The problem is, once you start assuming these unobservable causes, what's there to stop you at one unobservable cause? Maybe this is a structure of the world. Maybe there is a cause that causes shocks, a cause that causes tones, and they happen to occur at the same time every time. Maybe there are 8 different latent causes. So we want to model the learning process for the animal in some way that is tractable, that on the one hand can encompass the true complexity of the world, on the other hand does not confabulate latent causes for every single event that he sees. So what we did is we assumed what's called an infinite capacity prior, which is a prior belief. So the idea is that the animal comes to the world, comes to every new scenario. And when I say the animal, I mean the person too, because we're animals as well. We come to the world assuming some kind of structure of the world, and then we take in observations and try to fit them into the structure. And the assumptions here is that we have a structure that we call it a generative model. This is a model of how causes generate observations. So I get to see observations, but I have an idea of how they are caused in the world. And I have a generative model that is, as I said, flexible enough to capture complexity. So that's why it's infinite capacity. It has really large capacity, but it's constrained enough to allow learning. And when I say constrained enough to allow learning, that's because if I assume that every bit of information comes from its own latent cause, then I can never generalize. What I see tomorrow is not related to what I saw yesterday because the causes are completely different, so I can't learn at all. So I need to group things together somehow in order to learn. So the idea behind in words, this mathematical prior is this. So the idea is the animal is going to see trials in an experiment, so we'll work in trials. That each trial is caused by a single latent cause. Each latent cause tends to produce similar trials. So it has some characteristic probability of emitting shocks, emitting tones, emitting the odors that the animal smells, everything that is observable. The important property of this prior is this third property, which is that all else equal, a prolific latent cause is more likely to cause another trial. So this prevents the animal from inferring a different latent cause for every trial, because if one latent cause has already caused 10 trials, it's most likely going to cause the next one. So you try to group things together into latent causes that cause a lot of stuff. But you still need the flexibility, and that comes here in number 4, where the number of possible latent causes is unbounded. So the animal does not commit in advance that there are only going to be 3 latent causes or 4 latent causes. There's always some probability that the next trial is due to a new latent cause. So taking all of this together, this is also called the Chinese restaurant process prior. This is a prior, mathematical prior that was invented by people in, I believe, Stanford. That used to go to lunch at Chinese restaurants. And they had this image in their mind of an infinite Chinese restaurant where each table is a latent cause, and customers come in. Each customer is a trial. Customers come in. The first one sits at the first table. The second one sits with him at that same table. And people tend to want to sit at tables with lots of people. But once in a while, space runs out, and you start a new table. So that's a new latent cause. So this is just an analogy for the model that we are going to use. And so what we're really saying is, when we're thinking of conditioning in this way, what the animal is learning is in acquisition, when tones are followed by shocks several times, he learns that there's some latent cause that causes tones and causes shocks. But then in extinction, because things are so different, there are no shocks anymore, it's not likely that they were emitted by this same latent cause, because this latent cause tends to cause shocks. We've already seen that in the first trials. So the animal inferred that a new latent cause is in town, latent cause Y, and that causes the trials in extinction. So basically, instead of erasing the old learning, there's learning of something new, a new latent cause, a new contingency. And now at test, when we're asking the animal, are you afraid of the tone, we're not asking him, are you afraid of the tone? We're really asking him, do you think X is on now, or do you think Y is on now? And we can think of different manipulations, like giving a reminder shock as changing the likelihood that one of these is on, because they're unobservable. The animal has to infer this. So, sorry, just to be very clear about this. So the idea is that there is some latent cause here. It causes, let's say, trial 1, trial 2. Then there's another latent cause, causes a trial with no shock, another trial with a shock, whatever combination you want. This is the true generative process. But the animal does not have access to these latent causes. It sees only the observations and tries its best to infer what was behind them, so to try to recreate these latent causes. And mathematically, there are computational models that define the correct statistical way to do this. So Bayesian inference, or Bayes' rule, says that what you need to do is calculate for each structure behind here, each possible structure, how likely it is to have caused these observations. And then you can believe that the most likely structure, the one that was most likely to cause these observations, is the one that's that is really at play. Or you can just kind of hedge your bets and say 80% chance it's that, 10% chance it's a different structure, 5%, 1%. We're not requiring the animal to make a decision here between these structures. And here's another cartoon that shows you why it's really important to try to infer those latent structure. So what I'm going to do next is show you a couple of experiments, well, 3 experiments, in which we try to test the qualitative aspects of this model. So the first thing that we wanted to do is test the idea that animals cluster their observations into latent causes based on similarity, and that this kind of inference about latent causes sets the boundaries on learning, because once you start a new latent cause, you don't unlearn the old thing anymore. You learn about new things. And so we did an experiment in humans, our favorite kind of furry animals. And we showed them screens that looked like this. They saw many circles, and they had to guess how many circles are on the screen pretty quickly. They had 3 seconds. They had to type a double-digit number. So how many circles do you think there are here? 35, 40, 50. 47 is the true number, so 50 is the closest that I heard. So they would type in a number, and then we would tell them the true number, just like I told you, trial after trial. And what we were really interested in is not their ability to count, but their ability to learn from what we tell them on each trial was the true number. What is the average number of circles here? And that is because the average number of circles was drawn from a distribution, a Gaussian with mean 65 circles. But there was one trick, which is that trials came in 2 flavors. Some trials, all the circles were blue. Some trials, all the circles were red. We didn't mention anything about color to the subjects. We just said, tell us how many jelly beans are in the jar. But the blue trials always came from this Gaussian with mean 65. The red trials, it depended. So in some blocks, they came from, what you see up here, a Gaussian with mean 35, so quite different from the blue Gaussian. Whereas on other blocks, they came from mean 55, so very similar. And these blocks were, again, we didn't say anything about color to the subjects, but the subject could track this because it wasn't always red and blue. There would be, I'm calling them red and blue here for simplicity, but one block of trials would be red and blue, another one would be green and yellow, and that would be, green and red. So if they wanted to, they could track these different Gaussians. But what we had thought, based on our theory, is that in this case, in condition 1, because these 2 types of trials are so different from each other, they would separate them into 2 latent causes and learn separately the mean for each one. Whereas in this case, even though it's as easy in condition 2 to separate them based on color, because the colors are completely observable, because the number of circles is similar enough, we thought that participants would ignore color, lump them all together, and learn one mean, which means that if we compare their predictions or their counts on blue trials here and here, they should be more accurate in condition 1 than in condition 2. And that's indeed what we saw. So they were closer to 65, which is a true mean, in condition 1 as compared to condition 2. And this looks like a small difference, but it's significant. It's all within participant. So what this suggests to us is that in the simplest of tasks, humans, these sophisticated animals, are making inferences about the causal structure of the task. Because note that if they always took color into account, there should be no difference between the two conditions. Blue is always mean 65. And you can just learn that similarly in both conditions. And if they never took color into account, because we never said anything about color, they would obviously be less accurate in condition 1, because the overall mean there is, what is it? 35 plus 65, 50? The overall mean there is 50, whereas here it's 60. So the only explanation that I have for this is that people make this inference, and they don't necessarily make it consciously. In fact, I once gave a talk about this at Princeton, and one person from the audience raised her hand and said, I was a subject to this experiment, and until he talked about it now, I didn't even realize there were colors in the experiment. So, this is anecdotal, one person, but I'm not saying this is a conscious process. This is a subconscious process. So it's so subconscious that I think it happens all the time. So in general, bits of experience impinge on us. Sorry?
There were no extra cues.
Sorry?
Have we checked with people, for example, for seeing these colors? There were no extra cues. Even the colors were uniformly randomly distributed on the screen.
The colors were not randomly distributed. There were two types of colors, and the trials were either all blue or either all red. Yeah. Sorry for being unclear there. So what I think happens is, in general, as we walk through the world, bits of experience impinge on us all the time. And as I said, the whole idea of learning is we have to decide which things are of the same kind and which things are not, so that we can generalize. So we have to cluster our experiences together somehow into memory traces or latent causes or these clusters, and say, all these are of the same kind, so what I learn about one I can apply to the other, while these are of a different kind. And so we cluster them based on similarity, because no two experiences are exactly alike anyway. And so what we think is going on is that learning happens within these clusters, not across clusters. So these cluster boundaries delineate the effect of learning from one trial to another. So there's one part here that I threw in, but I haven't shown you yet, which is this idea that this has something to do with memory traces, that we cluster these experiences together in our memory traces in the brain. So the second experiment that I want to show you tests that directly. So what we did here, again in humans, is we gave them a different task that we now call the lines task. And in this task, subjects were asked to view small line segments and were asked to predict the next line. So let's say they draw this line with a cursor, and then we tell them, well, this was the line. You were pretty close. You earned 60 points. So now they have to predict the next line, and they predict it, and they see what it was, and they earn 80 points in this case. So these lines from trial to trial change slightly in angle and change slightly in length. And we're asking them to predict just because we want them to pay attention. Because what's going to happen, I'm going to move to the beginning of what I showed you. If you look here, this shows the subject what trial they're in. So this is trial number 5. It started from here, or trial number 4. And after they make the prediction, it moves to the next trial. And the very end of the block, this is the last trial. They earn 85 points. At the very end of the block, we move them back to the very beginning and say, can you reconstruct the line that you saw in that trial? It's not always the first one. It's one of the first ones. Reconstruct from memory. So this is a memory test for these little line segments. And the manipulation here was this. So what I'm showing you here is a depiction of the lines on each trial. So for instance, this dot here is a line of this length and that orientation. And you can see that they change The length changes a little bit, gets either shorter or longer on every trial, and the orientation gets either, the angle changes a little bit on each trial. So on some blocks, again, within participants, these changes were all gradual. So our hypothesis was because there are very small changes, all of these will be grouped together in some kind of uber memory trace, which means that all the lines will interfere with each other. And when at the very end you're asked to reconstruct the first one, there will be interference with all these memories. On the other hand, on other blocks, in the middle of the block, there was one jump that was just 4 times bigger than our regular jumps. We call these jump blocks. And we thought that on jump blocks, that jump would generate a new memory trace. So although there would be interference, the interference would be more local. These much longer lines at a different orientation would not interfere with the memory of this line. So subjects should be more accurate here than here. So once a subject makes a reconstruction, we can plot that here too. Let's say they reconstruct a line of this length and this orientation. We can measure the distance between their reconstruction and the thing that they're trying to reconstruct. Shorter distance is better. They're more accurate. And the distance to the end to see kind of how much interference the endpoint had, and longer distance there is better. And so indeed, that's what we see. So in the jump condition, the condition that we hypothesized would generate 2 clusters, their reconstructed line is closer to the start, which is what we want, and farther from the end, which is what we want again. And if we run our model here, in the jump condition, it creates or it infers 2 modes or 2 clusters, whereas in the gradual case, it infers a little bit more than 1. So what I've been telling you here, and what I think is going on, is that there's a constant battle between learning and memory in our brain. So we experience the world, and again here, the rat with the 3 trials of tone and shock, we'll put them all together in one cluster. But then whenever we encounter something that we didn't predict, that's not the same as everything that we've seen before, for instance, a tone without a shock, we have this choice, and now there's the high-level battle between learning and memory. Do I decide that it's one of the same, so I do what we call learning? I modify an existing cluster, I put it there, and if previously I thought that that tone caused shock with 100% probability, now it's 75% probability. I effectively overwrote my memory and changed it, and now my memory is not true to these first 3 trials anymore. It's the average. Or I can decide that this is different enough, and I put it in its own cluster. I start a new memory trace, and so we can call that structural learning. But using memory obviates the need for learning here, and I don't have to overwrite that memory and modify it. So the last test of this model goes back to the rat and the shocks and the tones and says, okay, can we use this to actually erase a fear memory, which was the original thing that we wanted to do. And the idea is simple. If prediction errors, if dissimilar data that I did not predict, is what leads the animal to create this new memory, to create a new state, and move its learning to that state, what I want is to get the animal, well, first of all, that would explain why extinction doesn't really work, right? Why extinction does not overwrite that old memory, and we can see 30 days later that that memory comes back. But we know what we want. We want to coax the animal to continue updating this memory, this cluster, and to put all these trials in that cluster. So the question is, what if we make extinction just a little bit more similar to acquisition? So it's not that different and does not generate the new cluster. So that's what we did. This is everything that I'm saying, by the way, is work by this student, Sam Gershman, the magical Sam Gershman. Did a lot of work very quickly. So he went to our colleague Marie Monfils' lab in UT Austin and ran an experiment on rats in which acquisition was, as I've described before, 3 trials of tone and shock, and each of these bars will signify a tone. In this diagram. And then in extinction, The first trial, he gave the animals a tone and a shock, and then a tone with no shock, and then a tone with a shock, and then 2 tones with no shock, and then a tone with a shock, and 3 tones with no shock, and so forth, basically coaxing them away from the shocks without ever really shocking them with the absence of shocks completely. And we call this gradual extinction. And we compared this to regular extinction, which is just the same number of trials, but no shocks at all in extinction. So our gradual extinction rats are getting 5 shocks in extinction, actually more than they got in acquisition. And our regular extinction rats are getting none. And we compared this to one more condition, which we called gradual reverse, that also had 5 shocks in extinction, but they started out quite spaced. So the idea was that here there's still a big difference between this phase and acquisition, but over time they became more frequent. In the end, we always had 9 trials without shocks so that the animal would stop freezing. Because what we're going to do in the test is ask either after a reminder shock, like I showed you before, or 30 days later. We had 2 experiments. Does the rat freeze at test more than they froze in these last 4 trials? And the test is just the tone, no shocks at all. And so again, our hypothesis was that in gradual extinction, because we're easing them off the shocks gradually, they won't at any point be completely sure that there is a new latent cause, and they'd continue updating that old latent cause. Whereas in these 2 conditions, they wouldn't. And so if you update that old latent cause with all these trials with no shocks, you're diluting the probability of a shock. And when you hear a tone again, you won't be that afraid of it because you'll think, it has a lower probability of giving you a shock. Whereas in this case, in the case of regular extinction, this latent cause will have 100% shocks in it and will not be diluted because you start a new latent cause in the extinction. And that's exactly what we saw. So on both tests, after a reminder shock or after 30 days, the gradual extinction condition is the only one that did not show an increase in fear compared to the end of extinction. Standard extinction and reverse gradual both showed very large increases in fear after a reminder shock, smaller but still significant after 30 days, and not significantly different from 0 in the gradual case. So, is it really 1754? No, I see. Yeah, that number's, yeah, that's good. I'm on the Israeli system where 70 is like, what is it called, military time? Okay, so what I've been telling you so far is that inferences about latent causes of observations, to my understanding, are an integral part of learning. And therefore, the structure of memories, if I could read it out from your brain, would basically, the clusters in your memory would tell me what you inferred as the structure of the world. Because we're trying to learn the true structure of the world. We're not just making it up. And that learning only happens within each one of these latent causes, within each one of these clusters. And in terms of reinforcement learning, the computational theory of reinforcement learning talks about this as states of the world. So the state of the world is, I hear a tone. But now I'm saying, no, the state of the world is, I hear a tone and I think that latent cause X is on. And that's different from the state of the world of, I hear a tone and I think that cause Y is on. Those are 2 different states. And so in the last part of the talk, what I want to talk about is, where are these states or inferred structures stored in the brain? And I want to introduce you to this area called the orbital frontal cortex. So the orbital frontal cortex is the area above your eyes, above the orbits of the eyes. You can see it here in a side view. It's down here. It's a very special area. It's strongly connected. It gets inputs from sensory cortices all over the brain. It gets input from subcortical areas. It sends connections back to many motivational and decision-making areas. But despite that, it's still not completely clear what this area does. In fact, this is the area that about 20 or 30 years ago people thought does nothing and sometimes would get rid of in lobotomies. Now we know it does things. What it does is it has a very pervasive role in decision-making tasks in the lab, but that role is subtle. So it's not that without the OFC, without the orbitofrontal cortex, animals can't do some things. They just do them slower, less efficiently, not as well as we see animals normally doing these tasks. And in the real world, it seems like this area is involved in making good life choices. So many people, unfortunately, get lesions in their orbitofrontal cortex. It's an area that gets easily damaged by car accidents. And Antonio Damasio described, and his colleagues described, a patient named Elliot, who after he suffered damage to the orbitofrontal cortex, divorced his wife, quit his job, and married a prostitute. You can decide which ones were the good life choices, but definitely his behavior changed quite drastically. This is all at the same time as performing well in lab tests of intelligence, reading, writing, comprehension, verbal fluency, etc. So this is not a person that you would look at him and say something is wrong with his brain, except his high-level decision-making is different. So based on a lot of previous data from animal studies looking at the effects of lesions of the orbitofrontal cortex and recordings from that area, et cetera, that I won't go into right now, we came up with the hypothesis, or I should say Robert Wilson, who was a postdoc in my lab and now has a lab at University of Arizona, came up with the hypothesis that the orbitofrontal cortex is the seat of these states, of this cognitive map of the task. And not only the cognitive map, but your current location in that map. Right now, the tone is on, and I think that latent cause X is on. That's what we thought would be coded in the orbitofrontal cortex. And we thought that this is especially true and important for states of the kind that I've talked about, these ones that you have to infer, that you don't directly see. So the tone, or here. So the tone sounds like the same old tone, but you know that this is different from that tone because you've inferred a different latent cause. Those kinds of states we think are critically dependent on the orbitofrontal cortex. We call them partially observable states. So the one last experiment that I want to show you is one in which we tried to test this hypothesis directly. And to do this, Nico Schuch, also a postdoctoral fellow in my lab, designed a task where the states would be unobservable. And here's how the task works. This is a task in humans again. So we show people a picture of a face and a house superimposed. And they have to make a judgment, make a decision about age. So is this face old or young? Or is this house old or young? We stretched our imagination a little bit. So old house is old-fashioned and young is modern. But they have to make that decision only on one dimension. And how do they know which dimension? Well, to start with, we tell them. So we can say, a new block begins now. You will start with face. Good luck. So you look at this face, and this face looks young. So this is not written on the screen. The subject knows in his mind or her mind that they are now attending to faces, and they make the judgment and say young. Okay, so comes a new trial, new stimulus. You're still attending to faces. This face is also young. Great. Next trial, you're still attending to faces. This face is old. And what we told subjects is, once the age changed, on the next trial, change dimension. So on the next trial, you judge houses. Again, this is not written. So you're going trial by trial and judging age of one dimension, keeping track in your mind what dimension you're judging, and keeping track of what was the previous age, because if the age changes, you have to change dimension. Now here, this house is young. I'm showing here two stimuli that are exactly the same just to illustrate that the stimulus itself can't tell you what you're doing. Here you were judging faces and it was old. Here you were judging houses and it was young, even though it's the same exact stimulus. I'm illustrating here one more thing, which is we told subjects, once you start a new mini block, once you started houses, for that trial you don't have to compare. So this basically starts a mini block of young houses, and only the next old house will move you back. The fact that this young was different from this old does not matter. You never compare across boundaries. So all these complex instructions mean that what people have to keep in mind when they're doing this task, and they do it really well, they do blocks of hundreds of trials without any error, without intervening. They start with about 20% errors on average. We train them a little bit outside the scanner for about half an hour on the first day, and then the next day they come in and we do this, and they do this inside an MRI scanner, and their average error rate is less than 5%. It's not that fast. I can't remember exactly what was the reaction time. If there was a deadline, it takes them about a second. The reaction time goes from a second point to from 1.2 to about 850 milliseconds. Sorry?
5, 6 neurons may be involved in how many neurons will be in sickle firing for this period of time. Right?
Yeah.
Store fire, right?
Yes.
They cannot do it in the real estate 200 milliseconds.
They cannot do it in 200 milliseconds. No. No, but we're not interested in the speed, and we're not interested also in making the task hard for them in terms of making the judgment. So there are only a few faces that repeat themselves. So we want it to be easy to say young or old. We want it to be hard to keep track of the state of the task, because the state of the task here has 4 different components. It has, what am I attending to on the current trial, face or house? What is the age on the current trial, old or young? What was the age on the previous trial, which I put here in parentheses, young or old? For instance, if it's this case, I know I have to change on the next trial. And what is the dimension that I attended to on the previous trial, face or house? Because if this was house, not face, I wouldn't have to change. So they're basically each of these can take on 2 values, so there are 16 states of the task, and the subject just has to keep that in mind. So we can draw the whole state diagram. And this is what it looks like. And the arrows happen based on the next stimulus. So let's say if you're in a house young, you're in a young house mini block, you've been looking at young houses. If the next house is also a young house, you stay in this state. If it's an old house, you go to this old house after a young house. And then you know that on the next block, you'll either go to old face mini block or young face mini block, depending on the stimulus. So they traverse this through the experiment. And so our first question is, can we see these states in the orbitofrontal cortex? These are states of the task. They're unobservable. We had hypothesized that a map of this task sits in the orbitofrontal cortex. So what we do is we try to decode on each trial based on the pattern of activity in fMRI, the whole pattern of activity in the whole orbitofrontal cortex. What state are you in out of these 16? And what our results show is that we can decode above chance is 50%, what is the current category that you're attending to, what is the previous category that you're attending to, what was the previous age. We can't, interestingly, decode the current age. We can't decode the current age pretty much anywhere in the brain. We can decode current category and previous category in other areas of the brain, but these 3 together, the previous age specifically, only in orbitofrontal cortex.
How big the region do you think?
This is a very big region. It's 4,000 voxels. Each voxel is 3 by 3 by 3 millimeters. Yes, lots of neurons in it. And we only have a measurement every 2.4 seconds. So this is very crude. And that's why you're getting, 53%. This is above chance, but it's not amazing. But I'll show you more amazing results.
The same for Orbital, the same location?
Sorry?
Same location for Orbital?
Same location. It's the anatomical mass.
Exactly within the frontal cortex. It's location with the same particular task, or task to be chosen for you to a different region?
So we looked at the whole orbitofrontal cortex for all of our subjects. We didn't ask within the orbitofrontal cortex where is each of them representing it. Okay? And this representation seems to be related to behavior in that the better we can classify the states in the orbitofrontal cortex, so the higher the classification here, the fewer errors the subjects are showing overall. But as I said, I'll show you something a little bit better, which is now, okay, so let's say we believe ourselves that the orbitofrontal cortex encodes these states, even though our decoding is not that great. It's, in frontal areas, nobody sees decoding that's much better than that. But in any case, what we can do now is look at the average activity. So every time you're, let's say, in the state, the previous one was face, it was young, and the current one is house, and it's old. Every time you're in that state, what is your activity in the orbitofrontal cortex? And we can average that activity to get one, the state of the orbitofrontal cortex when you're in that state. And we can do that for every one of the 16 states and correlate them and ask how similar is the state of your orbitofrontal cortex when you're in this state and, you know, in one of those up there. These are the same states. So this is a 16 by 15 correlation matrix. And we can treat these correlations as distances. So the higher the correlation, the closer these states are in your brain. And drawing these states as distances in 3D, this is what we get. This is the structure of the task in subjects' brains. So it's very structured. We did not expect it to look like this at all. And I'm coloring the states here in the same colors as I colored them here. But this is after I already saw that structure. I did not imagine this to start with. They used to be all gray before we saw the brain results. And what the brain results are showing us is this layer is the states of face young, house old. These are when I'm within a mini block. And then when I'm exiting that mini block, I go down to a green state. All the green states are the age it just changed. And then I go up to one of the purple states and back in. So this is kind of the way we traverse this. So that means that the state of entering a new block is very different from the state. These distances are 1 minus the correlation. The farther they are, the less correlated these states are. So what can we do with this except marvel at how beautifully organized it is? And I should say, take this with a grain of salt, because we recently realized that although everybody does these correlations in this way, there's a mathematical problem with that we're trying to solve. So it might be that this looks a little bit more structured than it should be. But even with that grain of salt, we can make predictions from this. This is the average structure over all subjects. But here, let me show you 2 subjects. This is structure for 2 specific subjects. One of them is our worst subject that had the most errors, and one is our best subject that had the least errors. You can try to guess who is who. They both saw the same task. And we can do more than that. We can say, let's look at all these transitions from green to purple. These are all transitions when you're changing blocks, you're changing attention. They're all similarly hard cognitively. You have to change attention. If anybody of you, if you study task switching, that's a task switching point. But some of them, some of those connections are, or some of those distances are shorter to traverse and some are longer to traverse. We can say, well, if it's longer to traverse, that means you're changing your neural representation a lot. That might take more time. That might be more prone to error. So indeed, if we take these 8 transitions for each subject and order them by how long they are, how far you have to traverse, the longer they are, the higher the reaction time of the subject. So that reaction time on that next trial takes longer if you had to change your representation more, and the more errors they show. So if you have to travel a far distance, you might end up in the wrong state by mistake. So we feel that, crude as it is, fMRI, millions of neurons in each voxel, 1 measurement every 2.4 seconds, and 4,000 of these, averaging over 4,000 of these voxels, still we can read out a representation that tells us something about subjects' behavior in a very precise way. In different trials, we can predict which ones will be faster and which ones will be slower. So this is not a causal manipulation. We haven't lesioned anybody's orbitofrontal cortex to see how the task changes. But to our eyes, this seems like this representation has something to do with how the subjects, I almost said animals, how the subjects are solving the task. So to summarize, the way I see it, as I've already said twice, all of learning is generalization, because no two experiences are ever alike. And so if we took that at face value, we would never be able to learn from any experience. But we do learn, so we generalize. And now we know a lot about how the brain updates values and learns what to expect. But we haven't asked before, and this is what my lab has been doing in the last few years and will probably be doing in the next many years, how exactly are these boundaries of generalization determined? And without answering that, we can't really understand how learning happens. And so we can understand reinforcement learning in the basal ganglia as a simple, you take a stimulus or you take a state and you update its value. But what we're adding to this is to say we need to think about how is this task or how are these states represented in our mind? How are our memories grouping different experiences, whether it's in the orbital frontal cortex or in hippocampus or dorsolateral prefrontal cortex? And how do these representations interact with learning, and also how are they learned themselves? Because in order to decide whether our representations are meaningful, we have to see whether they make correct predictions for our actions. So I'd like to thank the people who actually did the work. This is a rather old picture of my lab. Some of these people have already left and started their own labs. I talked mostly about Sam's work, Bob's work, and Nico's work, but everybody else contributed as well. Our generous funders, our many collaborators, and I'd like to thank you.